In this class, we try to add up bordered Hessian testing of the Roy's identity case where maximization of utility was tested in a previous video where we had examined Lagrangian multiplier method to find out first order condition FOC. First order condition that the marginal that the partial derivative must be equal to 0. The example we have already solved. Lagrangian multiplier method was used to the utility function with subject to budget constraint. We have already examined this and we have calculated fx is equal to y minus lambda px is equal to 0, fy is equal to x minus lambda py is equal to 0, f lambda is equal to p minus pxx minus py is equal to 0, and the finding of the x was equal to pyy upon px, y was equal to pxx by py, and so this was the first order condition was satisfied. We have to test its second order condition, and for that we will use bordered Hessian method. Bordered Hessian is a matrix method to optimize an objective function in fx and y, where there are two commodities. So bordered Hessian method is used for optimization, and the word optimization is used because in real life there are always limitations, constraints which we have to consider, and we have to maximize utility, we have to maximize output in case of firm. In all these cases, bordered Hessian will test second order condition. Second order condition can be tested through differentiation, differential calculus, finding out second order conditions, second order derivatives. But it is better to choose bordered Hessian method to find out whether bordered Hessian matrix result is greater than 0 or less than 0. Bordered Hessian is shown by this notation, and it is very easy to find out if we have partial derivative finding, that is fx is equal to this. For bordered Hessian, we will write down fx, fy, f lambda, fx, fy, f lambda, fx, fy, f lambda. Then we will write x, x, x. We will write y, y, y. We will write lambda, lambda, lambda. Then we will calculate it with this function, first order condition. This is fx, and what we have to find out second order, fxx. It means the function is further differentiated with respect to x. And here we find that fxx is related to neither this nor this. X is not there. Then the term will be equal to 0. Term will be equal to 0. Then second is fxy. Y is there. So fxy will be equal to 1. And then fx lambda. So lambda will be equal to 1. Finally will be minus px. So first row is 0, 1 minus px. Then we will find out second row that fyx, x is here, so we will get 1. Then fyy, nowhere y, second order will be 0. Then fy lambda, lambda is here, we will have minus 1 into py, that is minus py minus py. Then the second order, second row of ordered Hessian is calculated. Then the third row, fyx, third row, f lambda x, third row, f lambda x, So where is x? X is here. So it will be minus px. Then f lambda y, f lambda with respect to y is here. So this will be minus py. And then finally f lambda differentiated to second derivative, second partial derivative with respect to lambda differentiated, then we will have, there is no lambda in this equation, so this will equal to 0. So the third row is minus px minus py is equal to 0. Now we find out that its value will be equal to ordered Hessian will be this. So the first one will be 0, and in second one we will have, this is plus, this is minus, this is plus. So this is 0 but here this is minus, minus sign. We will have 1 and then we will have 1 minus py and minus px 0 and then minus px so we will have 1 minus py minus px 0. Minus 1 minus py px 0, then minus px 1 and 0, 1 and 0 and minus py minus py. Then we will have minus 1 minus px into minus py minus px, and we will have 0 into minus px minus then minus py. We will have minus px py minus minus 1 and this is 0 into 1 minus px into minus py. Then it will be equal to plus px py again minus px py and minus, then we will have only px py and here minus where we will have 0 minus px, this will be 0 and this is minus py. And last will be one into minus px first is minus Py, and this will be 0 into minus Ps. This will be minus Ps plus Ps Py. Then ordered Hessian is equal to 2px py, which is greater than 0. This is maximum. We know that in case of second order dx by dy, for maximum we write less than 0. But in case of Hessian, is the opposite. Maximum. So the sign will be just opposite in case of Hessian, bordered Hessian value. In second order condition, in case of calculus, ds square by dx square must be less than 0. Then there will be maximization. But in bordered Hessian, the value of bordered Hessian must be greater than 0. In this case, we have found that bordered Hessian is equal to 2px py, that is greater than 0. So maximum is satisfied. We have already calculated FOC, first order condition, that was equal to 0, which we have seen here. And then from the same question, we will add up this bordered Hessian to test second order condition, which is equal to Hessian, bordered Hessian more than 0. That is, in other words, that is second order less than 0 in calculus. And in matrix form, this is more than 0. Then maxima is satisfied. Bordered Hessian is most important method being used in order to optimize any function, and the objective function which we create to utilize Lagrangian multiplier and first order condition equal to 0, FOC equal to 0, we have calculated. In real life, there are many constraints, and if there are constraints, limitations, then the word optimization is used, because in real life, we have to maximize utility in consumer's choice theory, optimize production in forms theory, equilibrium of the forms or theory of forms. We will utilize bordered Hessian to examine and test and verify that the second order condition is satisfied or not. Here it is satisfied, so all calculations in Royal identity questions we have already discussed, that is being tested and verified, maximally verified. That's all. Thank you.